recorder. Here we go. So it's been recorded now. So if you did miss it or you want to watch it again, you can have a look at it. So this is on, just in case it doesn't come out that well, this is revision lectures on root loci, and it is question 4, the fourth question. And we'll go through how to do the exam question really. So it's in two parts. The first part is you're given a transfer function. This is a typical sort of one you might be given, about 1, 0 and 4 poles is usually what you get. And then you're asked to sketch a root loci. So we'll go through that first. Now, one of the things about this particular question is it lends itself nicely to a MATLAB solution as well. So as well as doing this maybe by hand, you might want to check it out in MATLAB, because you can check your answers. So that's a good. So we're going to go do two examples of these are past paper questions. I think this is 2018. Something like that. Yeah, 2018. This one. 2018. 18 is my lucky number. So this question wasn't that lucky though, but it was okay. So it starts off, you're given a transfer function and you're asked to sketch a root loci. And we've done a number of these. So the first thing it is, remember the bottom line are called poles. So these things are called poles. And the top line are called zeros. So we've got poles and zeros as the basic commodities in the root loci. And the first thing you do is you work at n, which is the number of poles. Now the number of poles is the number of s's you've got on the bottom. So there's one there, there's one there, and there's 2 there. So 2, 3, 4. So n is 4. The number of m is the number of zeros. So that's the number of s's on the top line, which is 1. And r is always n minus m, which is 3. Now, if you look at the past paper questions, they're always like this, and probably the same this year as well. But you can never tell, but probably. Then sigma is given by the sum of the poles minus the sum of the zeros divided by r, where r is this number here, 3. So we've got to write down where our poles are now. So we've got a pole here. This is at s is minus 5. This is at s is 1. If you solve this one, you get minus 2 plus 2j minus 2 minus 2j. So if we add those up, we get 4, 9, and 1 is minus 8. And it's got a 0 at minus 3. So it's going to be, this is going to be minus 8 minus minus 3 over 3. So minus 8 minus minus 3 will be minus 5. So it's going to come out as minus 5 over 3, which is minus 1.66, isn't it? So sigma is minus 1.66. Now, depending on the r number, you get things called infinite loci. And for r equals 3, you get an infinite loci that looks like this. It looks a bit like this. This angle now is given by 180 over r, and r is 3, so it's a 60 degrees. So the 60-degree angle there, that's a minus 60, that's going down there, and this distance where it starts is the minus 1.66. And again, if you look at, you can get different r numbers. If r is 2, there's 2 of them, and they look a bit like that. If r is 4, you get 4 of them like that. and the angle then is 180 over 4, which is 45. So you've got that's 2, that's 3, and that's 4. The one that tends to come up in the exam is this one here. This is a good one to remember. And so having got down to that stage now, we can now move over to do our sketch of the root loci. So I've done a little thing here for us. There we go. And the first thing we do is I'm just going to change my pen. Pens aren't working well, but okay. First thing I do is I plot the poles now as crosses. So if we go back over here, we've got poles at -5, 1, -2 plus a -2j. So there's our poles, 4 poles. We can plot those now as crosses over here. So we've got a pole at -5. I've got a pole at 1, so I've got a pole about there somewhere. It's gone off the screen. There's my pole at 1. And I've got another one, -2j, so it's going to be 1 there and 1 there. So I've got 1 up here, and there's another one down here somewhere, but I can't quite fit it on my camera. I can't quite see that far. Anyway, there's our 4 poles, and we've got a 0, and the 0 was at -3. So we can put that one as well. And so that's going to be 0 is a dot with a circle around. Then what we do is we put our infinite root loci, so that's this thing here now. So let's work into all this. One of these, we put one of these on now, and that distance is -1.66 because that's the sigma. So put three of these on. This is 60 degrees, and it's at -1.66. So back to here. So -1.66 is about there, isn't it? Let's just get everything on. It's about there, and then we can get our protractor then. If you need to do this question, you'll need a protractor. You don't need to go to shops. I made this one, just printed it onto a bit of glossy paper and made it. So this is quite easy to make. Save a bit of money. And you go to here now, measure out 60 degrees. So 60 is there, and -60 is there. So that gives me 2 dots for my 60 degrees. And that allows me to draw on these infinite asymptotes. A bit like this. And another one going down that way. So there's 2, there's another one going down that way. There's point in drawing that one on. So we're getting on with this now. So next thing is we do root loci now on the real axis. So what we do is we start off on this side over here and we move along, and as soon as you meet a pole or a 0, there's a root loci on the real axis until you meet 2 things when it switches off. And then so the rule is if there's an odd number of things, there's root loci. You add up poles and zeros like you add up fingers, and if the number's odd, there's root loci on the real axis immediately to your left of the last thing you've counted. So here's one thing here. It's not the number 1, it's 1 pole. That's an odd number of things. So there's a root loci here. I want to get to here. There's 1 thing, and 1 thing is 2 things. 2 things, even number of things, so no root loci there. By the time we get to here though, get 1, 2, 3 things. Now 3 things, odd number of things, and therefore there's a root loci there. So this is our root loci on the real axis. And then what we know is that m poles, that's 1 pole, m poles go to finite zeros, and r poles go to infinite zeros. These lines here, these things here are infinite zeros, and these things over here are finite zeros. So we know now that 1 thing goes to a finite, so this pole goes to this, or this pole, sorry, goes that way into this finite 0, so it goes this way. like this. That's the direction it goes, because it always goes from poles to zeros. And then the 3 remaining poles, that's this one down there, and this one over here. These 3 now, I'm moving this down rather badly, they go to the infinite zeros. So this one will just go straight down that line because it's on the infinite zero straight away. Now this one has to go towards this line here that I drew, and you can't see it very well because my pen wasn't very good. That's the infinite zero there. That's that minus 1.66. So this one's going to approach this. So it's going to go like that, and the other one's going to go like that. And then that's my root loci plot in total. It's symmetric, this, so we don't. So we've got basically a pole at 1, and that goes that way to the minus 3. This one starts here and goes towards this asymptotic line here, and this one goes towards that one, and that one goes down there. And that's our root loci sketch. And for that, probably I'm going to give you, say, 8 marks. Okay, that's a typical sort of thing you might get in question 1. Now let's. I think I've got a sketch of this somewhere. What we could do now is we might want to check now they've done this correctly, because I might be a bit worried we're not doing it right. So what we could do is we could go back now to our original transfer function, and we could enter now this function here into MATLAB, and we can MATLAB to plot this out for us over here. Or not plot it out, but you could plot it on your computer, couldn't you? So it'd be handy now, given that we're doing this exam at home, to also know how to do this in MATLAB. So I'm just going to rub this little bit out here. Not doing very well at rubbing out here for some reason. Just get it nice and dry. I've seen a really big spider in my garage. But anyway, right. So let's move to that actually. So if we got this function now, which is you think of it as 10 over s plus 5, say, and we think of it as s plus 3 over s minus 1, and the last bit could be, say, 1 over s squared plus 4s plus 8. So you can think of our little system that could break it down into subsystems like 10 over s plus 5, s plus 3 over s minus 1, 1 over s squared plus 4s plus 8. And we could call this, say, sys1, this sys2, and this sys3. And then we could enter these into MATLAB and then get to plot the root loci. So this is how we would do that. We'd put, say, n1 equals 10, d1 equals 1. Remember, these are in square brackets, and sys1 equals tf n1 d1. The tf stands for transfer function, and that's got that one in sys1. We do the next one. n2 equals 1 3. That's the 1 and the 3. And say d2 is 1 minus 1. That's the 1 and the minus 1. I could put, say, sys2 is tf into d2. I'll put the rest of the code here for you. Then put this one in. I can put, say, n3 equals 1, and d3 equals, it's quite handy now, it's going to be 1 4 8. So although it's a polynomial, remember to put some spaces in there, 148, and then sys3 equals tf and 3d3. And then we multiply the 3 together by saying sys4 is sys1 times sys2 times sys3. That would all be on one line. And then our locus sys4, and it would then plot the root loci for us. And we could then check that what we'd done was correct. So we've entered this one, and that one, put them in, multiplied them out, and then done our locus command. So that's how you could do the same thing now in MATLAB to get a similar answer. Okay, so that's what I'm going to do. Is I'm going to do another example of sketching a root loci as a past paper question, and then when we've done that, then we can use the second part is finding out when the system goes unstable from the root loci plot. So we're going to do that separately. I just need to get the board nice and dry, otherwise it'll go wrong for me. I'm just going to move the camera slightly that way as well. Just well done to all Man United fans. It was a very good win, wasn't it? 6-2 against Roma. I thought they were going to lose at one stage, but they didn't. That's just another past paper question. I'm just going to risk changing my pen. This is the last lecture of the year for me, so my pens are on their last legs as well. So this one's got a transfer functionality, so GS, what's quite good in this, 6 S minus 1 over S plus 1 S plus 5 S squared plus 6S plus 18. I chose this one because it was I thought it's a good one for revision purposes. This you might get something like this but with different numbers in. This could be quite a good one to have a look at. So let's have a go at doing this one, shall we? So it's a standard procedure. We work at N, M, R and sigma. So N, number of poles, 1, 2, 3, 4. M, number of zeros, 1, R, 3. So 4, 1, 3. And sigma N is the sum of the poles minus the sum of the zeros divided by R. So to get our poles and zeros over here, poles and the zeros. Then got a pole at -1, -5, -3 plus 3j, -3, -3j. That number there is half of this one, and then that one it's a complex conjugate a squared plus b squared, so you can see that 3 3s are 9, 3 3s 9, 9 and 9, 18. If you get some numbers, it'll be easy to do. And it's got a 0 at 1. So this comes 5, 6, 7, 8, 9, 10. This comes down to -12, and that comes out as 1. So sigma is -12 minus 13 over 3, which is -4.33. So in that particular case, sigma is -4.33. But we also know, because R is 3, it's got one of these 60-degree infinite zero things. So I can't quite fit that in here because I haven't got any space away. But do it here, let's try to get a bit of space here. So it's going to be one of those because R is 3. I think most of the time R is 3, occasionally R is 4. You wouldn't get R is 2 because it's too simple. So it'll either be 3 or 4, but 3 would be a good number. I don't think Everton beat anyone 3-0 this year. It's a shame, but they could have. They had a bit more luck. But they're unlucky really all season. No, they weren't really. They were very lucky, Everton, to get where they were. They played really badly. So next thing, I'm just going to do some little sketch. If you're doing this as an exam question, it doesn't have to be that accurate, so you can just do it straight onto a piece of paper using a ruler. You don't need graph paper. It's only a sketch at the end of the day. -1, -2, -3, -4, -5, 1, 2, 3, and okay, so this is similar to what I had before, but different as well. We go over here now, so we've got plot the poles, -1, -5, -3 plus -3j. So that's going to give us a pole at -1, -5, and another pole there, and another pole down there. I can get to see all this. So that's my -3, -3j. I've got another one down there, but we can't see it because, well, you can see it, but it's hard to fit onto the board. And then we've got a 0, and we get 1 0. We've got a 0 at 1. So 0 at 1, because s -1 equals 0 gives us s is 1. So we've got a little 0 at 1. Like that. Last time we swapped those over. That was the difference. Right, so then we can do root loci and real axis. So it's very similar to the last one. This is one thing here, so you get a root loci there. This time it goes from poles to zeros, it goes in that direction. Last time it was going this way, this time it's going that way because it always goes from poles to zeros. And then we'll have another one going down here, like that. It's because it's a 1 thing, odd root loci, 2 things even, no root loci, 3 things, odd root loci. And then we've got to put our sigma on. Remember that the sigma is -4 over 4.33, so let's put that on as well. So -4.33 will be about there, and I'll draw an angle of 60 degrees in. It's probably about there somewhere. Like that. And then another one going down like that. So there's my, I can match all of those on the board. The pens are going a bit sort of, anyway, let's go back a bit. You can see the cross there. So the last thing is now, 1 pole goes to a finite 0. That's this one going down that way. And then the 3 poles, that's because R is 3, remember, go to infinite 0. So this one goes down that way. This one approaches the asymptotic line that way. And that one approaches the asymptotic line that way. So I can take it back a bit. It's just not got the right sort of colour scheme here. The lighting's not good for this. But anyway, that's what it looks like. So 1 goes that way. 1 goes, I've probably done this too big. A bit smaller would have been better. This one goes up, approaching this asymptote, and the other one goes, there's an asymptote going down there, and the other one goes down, approaching it, like that. And that would then be the root loci sketch for the system. And again, that would be worth, it's not worth a lot of marks, but it's worth 8 marks, isn't it? 8 marks isn't too bad. And again, I did this one in MATLAB. They're not good enough to show you because the focus isn't good on my, it's not bad though, is it? It's not too bad, but I don't think it won't show what I want to show. Right, so let's just have another quick go at doing that again. I just did it a bit smaller. I think I've been too ambitious and tried to use too much of the whiteboard, and it doesn't actually work with this particular camera. It works well with my Samsung, but not with this particular camera. Just a bit inferior. If we're still going online next year, I shall invest in a super duper camera, a 4K one. That gives us the accuracy that we need and better definition. And you can spot all my grey hairs and everything with it, because it'd be that high quality. Let's see how if we've done this in MATLAB. The transfer function was, say, 6 over s plus 1. S minus 1 over s plus 5, and let's say 1 over s squared 6s plus 18. So that was this was the transfer function we had. So again, we did the same sort of thing. Call this one sys1, sys2, sys3, and we could then input this into our MATLAB and get it to do the root loci for us. So we put, say, n1 is 6, d1 is 1, 1, sys1 is tf, n1, d1. They're round brackets, these are square brackets. Then we could put, say, n2 is 1 minus 1, d2 is 1, 5, sys2 equals tf, n2, d2. And then I could put, say, n3 is 1, d3 is 1, 6, 18. That's the 1, 6, 18. And then sys3 is tf, n3, d3. Then we could put, say, sys1 or sys4 equals sys1 times sys2 times sys3, and then r locus sys4, and that would give us the root loci sketch. And you can have a bit of code like this pre-written before the exam, and chances are you just have to change some numbers like the 6, the 1, that number, and those numbers. So it wouldn't have that much to change. You could do it in a flash, and then you could plot out a root loci, and that's going to be handy because if you've seen it, it's always easier to do, isn't it, and make sure you've got it looking perfect. Okay, so that's how you could do the same thing using MATLAB. Now, the second part of the question is always, if we have this system here now, and we want to find out the range of gain of which this system is stable. So if we put it under closed loop control, we put the system under closed loop control, and this, then for some values of kp it'll be stable, and for other ones it'll be unstable. And we can get these numbers now. We could have done it using Hurwitz, but we can get these numbers off the root loci sketch that we did earlier. So we have to go back now to our root loci sketch, but interpret it in a slightly different way. So I'm going to redo my root loci sketch over here, and then we're going to use now the angle and magnitude criteria. Use the angle and magnitude criteria to find out the range of gain over which this is stable, and this is usually part B, and it's good for 6 out of 20. There's part C, which we'll look at after this. So, in order to do this now, we'll have to go back to our root loci sketch, which I'm going to make a little bit smaller, I think, than I did before, because it was too big. So let me just have a quick look at this. So I'm just going to do a quick root loci sketch. So it's got a 0 there. It's got a pole there. There's a bit of root loci there. It's got a pole there, and that's going like that. And it's got another one here going like that. So this is what the root loci, that's what the root loci sketch looks like. Now, the interesting thing about the sketch now is this. Any point where the root loci crosses this line, where it can go unstable. So it crosses it in 2 places, here and here, 2 places. So we need to work out now we need to figure out where this point is, and that will give us a KP1. So we'll figure out where that point is and what the gain is, and also figure out what we know where that point is because it's at the origin. And we could work out a gain here, KP2. Now, because the way the root loci is going, this one's going that way, so it's going to go unstable that way, and this one's going this way because it goes from poles to zeros. This is going unstable as well. So let's say that was 10 and this was 5, then the 5 wins, doesn't it? It's like, say you go drunk at 5 pints of beer and also go drunk at 10 pints of beer, the 5 will kick in first, won't it? So this will be the winner. If this is, it'll be the smaller of the 2 that's the winner in terms of the gain that goes in there. But we'll have to now work out KP1 and KP2. So in order to do this now, we're going to have to use the angle criteria. And so we'll just go for KP1 first. So this is like a guessing game now. Now, if you've done this in MATLAB, you'll know where this point is, because when it's sketch point, you can put your mouse on there and it'll tell you where it is exactly. But if you haven't got MATLAB, then it doesn't matter, because you're not meant to use MATLAB anyway. It's just a bonus. But you have to find this point now, so you make a guess. So somewhere up here somewhere, you can see that's -3 plus -3j, so it's going to be higher up than -3, isn't it? And so choose a point. So we guess a point, and then what we do is, having guessed the point, we draw straight lines from that point to all the poles and zeros. So I get my little ruler now. This is where you guess. This is a guess now. Unfortunately, it's a guess. But as I say, if you've got MATLAB at hand, it minimises the guess because you can guess it right first time. Then draw some lines in. The poles and zeros. So I've drawn lines in now to all the poles and zeros from the point I've guessed, and then we start measuring the angles now. So remember, to measure the angles, you're going to need a protractor. Now notice this is a good trick. This here looks quite small, doesn't it? But here looks really big. That's a trick you can play with the camera now. You can change the size of whatever you've got by moving it in and out of the camera. Handy that. So now, if it's a 0 angle, the zeros we label as alpha I, and the poles as beta I. So this is an angle here, which you can measure. It's a 0, so that's alpha 1. Then this one could be beta 1. That one there could be beta 2. This one here could be beta 3. And that one there could be beta 4. So we've measured those angles now using our protractor, and then we can then check if the angle criteria is true or not. Now, the way we check the angle criteria is that the alpha, sum of the alphas minus the sum of the betas has to equal to minus 180. So in this particular case, it's going to be alpha 1 minus beta 1 plus beta 2 plus beta 3 plus beta 4 should come out exactly as 180 if this point is on the root loci. If you've guessed wrong, this will come out as some other angle, like 160 or 200. But if you've guessed spot on correct, this will come out as exactly 180, and that then locates the point for you. And once you've located the point, that's using the angle criteria. We can then use the magnitude criteria to get the gain. And the magnitude criteria is fairly straightforward as well. We go back to the diagram and we measure the distances. So we measure from there to there. Because it's a 0, I'm going to call it M1 hat. We can then measure from there to there. I'm going to call that M1. From there to there, that distance can be M2. From there to there can be M3. And from there to there can be M4. So we could measure those distances now using a ruler drawn to the scale that you've drawn the diagram to. Then you can then go back then into the magnitude. Now the magnitude criteria, if there's a number there, you have to include this number in. So it's going to be Kp times 6, that 6 has come from there, and then it's going to be M1 hat, that's the 0 distance, divided by the product of the pole distances, which happens to be M1, M2, M3, M4, and that's always equal to 1. And you solve that then for Kp. Now, when you do that, Kp comes out as Kp comes out as 111. So Kp1 comes out as 111. If you've got your, if this is done this in MATLAB, then you'd have got, you can't see it very well, but you'd have got a root loci sketch here. And if you moved your mouse to this point here, that's like you move your mouse, you know, this is your mouse here. Looks like one of these things. My Tesla mouse, this. You can't see it real. I know it's a mouse. And you move your mouse so the cursor sits on this point. It'll tell you what this number is in the little box. So in my case, it came out as 111. You can't see it very well because this hasn't got autofocus. You just can't see it there, can't you? There, 111. Anyway, it comes out as 111. So that's the first bit. This is where it's handy now if you've got this in MATLAB, because it will give you this answer as well. Save you some of the sweat on this, or this to check the answers. So make sure that Kp comes out close to this number. That's giving you one number. Now that's the first part. So that's giving us one number. So as it goes unstable now, increase the gain. When it gets to 111, it starts to go unstable. 112, it's gone unstable. We've also got this one here to worry about. So this one, we have to come back to this one now, because it's also going unstable this way as well. So we've got to work out Kp1, but also got to work out Kp2 as well. So let's concentrate on Kp2 next, shall we? It's easier to do. And I'm going to start again, because the diagram will get too confusing otherwise. So usually in these questions, I set them up so the root loci crosses twice, and you have to do the calculation twice. So this is a good example of what you might get, which is why I've chosen it. So I'm just going to quickly sketch this again. And it's not coming out that well, so I'll just swap my pen. Good. I almost got a spider then, but it ran off. Right, so look at this. So we had a 0 there, that 1. We had a pole at -1, another one at -5, and then we had some -3 plus 3j, -3 minus 3j. So there's our. Now the interesting point, we're interested in this point here now. So this is a bit easier to do. That's that distance there. That's from the 0, so that's going to be m1 hat. Then from there to there, that's going to be m2. Then from there to there, I'll just draw it like that. That distance. That's going to be m3. So that was clearly m1 is 1, m2 is 1, and m3 is 5. It's not the size, it's just a distance, like a modulus. This is a modulus equation, so the size is more important than the sign. And then the last one, we'd have to draw a line from there to there, another line from there to there, and that distance is going to be root 18, isn't it? That's going to be root 18 as well. So we can stick the numbers into this more routinely now, can't we? Because we know that we don't know what that's his KP2. So M1 is 1, M2 is 1, M5 is 5, and M2 times M3 is root 18 times root 18 is 18, isn't it? So it comes out as 6 into 18 goes 3, and 3 5s are 15. So KP2 should come out as what did I say? That goes into that 3 5s are 15. So KP2 will come out as 15. So we know that value there was 15. And then we've got the other one, 111. So imagine now you've got some drinking competition, and this is going unstable, goes unstable at 15. And this one, this is say 15 drinks. And this one goes unstable here at 111 drinks. So clearly the 15 wins, doesn't it? So in this particular case, KP would have to be less than 15. If you kept it less than 15, it'd be on this side, it'd be stable. Which formula? I'm not sure which formula you want now. You said, can you show the formula again, please, to know what formula for KP2? Yeah, it's just going to be, it's the same one as we had here. It's the same equation, just different numbers in it. So it's going to be the 6 or KP2 times the 6 times M1 hat over M1, M2, M3, M4. It's exactly the same equation as we had before. It's the magnitude criteria works anywhere. So KP2 we don't know, 6 we don't know. M1 was 1, M1 hat was 1, M1 was 1 as well, M2 was 5, and M3, M4 was 18. That's where the numbers came from in that one. For this one, you can always work them out in your head. But for this one, and you know where the point is, you have to guess. You don't need the angle criteria for this because you know where it is. It's definitely the origin. So therefore, you can just apply the magnitude criteria, and working out these distances is easy. Whereas here it's more tricky. Okay, so that's that one. And you could have done the same thing now for that one we did previously. That is, this one is 2017. But I thought it was a good one to have a look at. Hint, hint. 2017. So that's part B of the question now. That's a typical solution to part B, and this is a good part B, you could argue. And again, if you'd done this in MATLAB, you could have clicked there and clicked there and got these numbers out, so you could have checked your answers. And you could do it in about, you'd probably do it in about 2 or 3 minutes, couldn't you? So it's probably worth doing, because then if you know you've got a question right, it always gives you a bit of a boost, doesn't it, that you've got a few more marks. If you did this slightly wrong, I could still give you like 5 out of 6 for it if you made a few blunders. But if you did it completely wrong, you couldn't get anything, could you? If you just drew a picture of Dr. Houlihan and said, I could give you 1 mark for that maximum, but probably struggle to give you a mark in reality. Now the last part of the question, part C, I want to look at that one next. There's 3 parts to this question. First of all, sketch root loci. Secondly is find out where it crosses the imaginary axis. And then the third part is, I can explain that one next. We've done all these, but explain the third part now. Right, I'm just going to sketch the root loci again to show how the third part works for you. This pen's gone. I'll just get a better pen. I bought 20 of these, so they've done well. I think they were about 50p each, these, but they've done well for me, to be fair. They got a bit tired over Easter, but then recovered over Easter. I'm just going to rub that a bit. Right, here we go. Let me explain part. This is the third part of the question now. So let's put the root loci sketch on first of all. So what we've got is, so that looks a bit, I'm going to do it fairly small. So there's our root loci sketch, and probably these will be further back from that. I'm just going to move these back a bit. Look on there somewhere. There we go. So there's our root loci sketch. That's the 1, that's -1, that's -5, that's -3 plus -3j coming from the transfer function. Now these roots here are called the dominant complex roots. And the reason they're called, well, they're the only complex roots there, aren't they? Everything else is a real root, so these are the complex roots, and they tend to dominate as well what's going on. So this part of the root loci is called the dominant complex root. And along here now, as you go along this line, the dominant complex roots will have a different damping ratio. Remember the equation for second order, these are representing second order systems, which represent s squared plus 2 zeta omega n s plus omega n squared, going back to our second order system work. And here's the damping ratio. As we go along here, the damping ratio changes. Now, if I draw a line, a straight line, from the origin up like this, from the origin like this. This line I've just drawn on, you can't hardly see it, can you? I'm just going to get swap pens. This line here now is called, this line here, this is called a constant damping ratio line. So this is called a this line is called a constant damping ratio line, and the value of the damping ratio, if we call that angle there theta, then cos theta is equal to the damping ratio. There's the little equation that relates damping ratio to theta. Now, for a lot of flight control systems, a damping ratio of 0.5 isn't too bad. It's not brilliant, but it's not too bad. So if the damping ratio is 0.5, cos of the theta is 60 degrees. So if damping ratio equals 0.5, theta equals 60 degrees. Where do you know where to pick the intercept from the graph? I don't know what you mean by that. Just bear with me for a second, okay? Then it all might be understood. So in the part C now, you're given a damping ratio, and I like 0.5 because theta is 60 and it's easy to draw and measure 60, isn't it? But it could be 0.6, but chances are it'll be 0.5. Most of the past paper questions are 0.5. So you know now theta is 60 degrees. So you could draw a line now, this line along here, and you could make that angle equal to 60 degrees. Okay, remember, to get 60 degrees, you'll need a protractor. Notice it's quite a small protractor, this one. Whereas if I've got a new protractor, it's much bigger, this one. And this protractor I've got is quite small. So, in part C, you're given a damping ratio, usually 0.5, which implies a theta of 60. And you draw this line along there at 60. Now what you've got to do is find that point and find the gain at that point. That'll be the gain then that'll give you this damping ratio. So to do that, we just use the angle and magnitude criteria. And when we found this point here, we went up and down this way. This is exactly the same. The difference is you go up and down here. So let me explain how we can do that. So we've drawn this line in at 60, and we know the root loci is somewhere along this line here. We don't know where yet. So in order to find this now, we're going to have to use the angle criteria. So to apply the angle criteria, what we do is we guess this point, and we draw straight lines from that point to all the poles and zeros. So we can draw this line in here. So the line's got to be along this line. It's not good choosing here or here. It's got to be on this line. And again, if you've done this in MATLAB, you could have run your mouse along there until the damping ratio became 0.5 and it would have given you the answer. So if you've got MATLAB working, you could have helped yourself a bit. But if you haven't, you're not meant to have it. So then draw that line in, then draw this line in, then draw that line in. This is to all the poles and zeros now. Draw that line in and draw this line in, like that. And then we can now apply to this diagram the angle criteria. So what it said was that there are zeros given by alphas and the poles by betas. So measuring this angle here using the protractor, and that'd be alpha 1. Can measure the angle there, and that could be alpha 2. Could measure the angle there, that'd be alpha 3. I could measure this angle here, that'd be alpha 4. Now to get this angle here, we've got probably the safest way of doing it is to, well, this one's below the line, so it's a bit awkward. So you've got two ways of measuring. You can go around that way as a plus beta 4, or you could go that way as a minus beta 4. Both would give you the same answer, but you've got to bear in mind which way. If you measure that way, it's positive. If you measure this way, it's negative, because this is negative measurement, isn't it? Say doing a plus 10 or plus 20 is that way, but minus 20 would be that way. So it depends on which way you want to measure. It's up to you, it doesn't make any difference. You stick these angles now into the angle criteria and hope for it to come out as 180. So it's going to be alpha 1 plus beta 1 plus beta 2 plus beta 3 plus beta 4 equals minus 180. And if it comes out as 180, you know that point's correct. If it hasn't come out as 180, you'll have to move it up and down that line until it does come out as 180. Now, in my case here, beta 4, I've assumed we've measured around that way because it's a plus sign. But if we've measured it that way, that would have to become a minus beta 4 because it's a negative angle in your calculation. But it gives the same answer, doesn't it? Because the phase of that angle is plus beta 4 or minus beta 4, depending on which way you measure. And so then you could then move now. You can see if it came out to 180. Now in the exam, as long as it comes out as about within 5 degrees, you won't get it spot on. So as long as you get within 5 degrees, that'll be enough, good enough. If it doesn't say it came out as 170, then that would be a bit dodgy. So then you'd probably want to move it up a bit. If it's low, you move it up. If it's high, you move it down. So you move it up a bit, have a new guess point, and then do it again. It'd probably come out quite close to 180. Yeah, sorry, I made a mistake there. Lost my brain here. That should have been beta 2, shouldn't it? Beta 2, that should have been beta 3, and that should have been beta 4. Well spotted. Or beta, sorry, beta 1, beta 2, beta 3, and this should be beta 4. Yeah, this was the alpha for the 0, and then the poles have betas. So thank you for that. This is the alphas are, you measure angles positive that way, don't you? So that the alpha is going to be positive anyway. That's going to be positive, that's going to be positive, that's going to be positive. If you measure right the way in that way, that would be positive. If you can measure that way, it's negative. It's quite straightforward. But then if you use the minus beta 4, put a minus in there. You need to practice one of these, don't you, to see that the numbers come out. You don't want to be guessing this on the day and thinking, oh shit, I wish I'd done this better. Just have a practice. This is a good one to practice. That's why I've chosen it. Now, once you've located the point, you can then use the magnitude criteria to work out the gain. So if we do away with that for a second. So then what we do is we'd measure now from there to there. So that'll be M1 hat. Measure from there to there. That could be, say, M1. Measure from there to there. That could be M2. Measure from there to there. That'll be M3. Measure from there to there. And that'll be M4. It's minus 180, that's what's minus 180 there. Yeah, see, sorry, I made a mistake on this. I've lost my way here. It's the sum of the poles minus the sum of the betas is equal to minus 180. Yeah, you're right. For some reason, I've lost concentration on some key points here. Sorry. Remember, it's the sum of the zero angles minus the sum of the pole angles is equal to minus 180. We'll get there eventually. And then the this equation, the angle criteria, is always true whether you're going up and down here or up and down here. And so the magnitude equation we read previously is also true. So it's going to be Kp times 6 times M1 hat over M1, M2, M3, M4 equals 1. So this is exactly the same equation, you're just sticking different numbers in. And then that'll give you a Kp, which will give you the gain at this point, which will give you the damping ratio on the complex roots of 0.5. And that'll be part C, and that's good for another 6 marks, so it's an 866. And this is a good example, this one. This type of transfer function is a good example, and you can just imagine some different numbers in there. It won't be these numbers, but this type of one could be a good one to revise and have a practice out. So I'd recommend this one as my number 1 to have a go at. It's probably the most useful one. Okay, so that's this type of problem looked at, really. You've got, there's 3 parts to this. Sketch root loci, find the gains when it goes unstable, and then find the gains to give you a certain damping ratio. So the second and third part are using this angle and magnitude criteria, and the first part is your root loci sketching rules. And as I say, if you have a computer with MATLAB on, you could always check your answers, couldn't you, quite quickly using this method of MATLAB. So I don't want to over confuse the story, really. I want to try and keep these revision lectures short and sharp to the point without sort of going off on something that won't come up in the exam. I don't want to put any red herrings in or anything for you. So this is a good example. Obviously this isn't the question, there'll be a different question, but this is a good example to practice at. And that's my top recommendation for today. Any questions? I don't particularly want to do any more examples because I think this is a good example to have a look at. So what I'd recommend is see if you can do this in MATLAB, see if you can get these answers out, and then having got the answers out, try and do it by hand as well and get the same answers out. And you should be able to do that, and then that'll be excellent revision for you. You won't get any better revision, really. There's still you've got to know what you're doing, haven't you, with this? And you've got to use a protractor, measure angles and that sort of thing, and measure distances and know all the equations. So there's a bit to do on this question. It's 3 parts. Each part will take you about 10 minutes, probably, won't it? 10, 15 minutes. And that's my 4 questions now. So we've done our revision. And there's nothing much more that I can say without, I think that's as much as I can tell you. The exam starts at 9, finishes at 4. Have a practice at like taking pictures of you. Do it on plain paper if you can. Lined paper isn't quite as good, because you can add it on lined paper, but it's just easier to mark if it's on plain paper. Put page numbers on, I would, in case it goes wrong, so then we know what pages are which. And practice taking a photograph of each page and then putting it into a PDF file and sending it to somebody. Practice that beforehand, and you've got to hand it in by 4 o'clock. If you don't make 4 o'clock, don't panic. You can still hand it in within the next quite a few number of hours. But if you do hand after 4 o'clock, make sure you put a PMC in saying that you had internet problems. And it's got to be within the 24 hours. So you've got to do it by 9 o'clock the following morning. You've got to get it in and then put a PMC in as well. That's the regulations on handing stuff in. So that's us done now. This is like, as I say, a nice little example for you to practice on. So we've done all the revision, we've done all the course stuff. Hope you find the course interesting. If anyone's interested in like flight control projects, I've usually got about 6 flight control projects to run next year. So hopefully we'll be able to do some experimental work in the wind tunnel. So if anyone's interested in like flying little drones, I've got loads of those little drones. You could have a finally a project running flying a drone at home. They're only about 50 or 60 quid, £100 the drones. You could borrow one for a year, use that. But no, that's just if you want to do a project on flight control. But I'm sure there's other projects like aerodynamics with Dr. Shuka Gabor or flight dynamics with Dr. Hoolan. You could also contemplate. But good luck now with the exam, and hopefully I'd start teaching you in February next year. So hopefully by February next year there'll either be no COVID at all, or COVID-5 will be out and we'll all have to be at home again. You can't, it's a 50-50 I think, isn't it? 50-50 chance of either. So 50-50 chance that we'll be reunited in Newton next year, or still on the whiteboard here. It's a 50-50, like a toss of a coin. I think Man United have got a better chance of winning the Europa Cup than we have for getting in, because they've got a good chance, haven't they? They must have a good chance of winning that, like a odds-on favourites. So good luck, you Man United, and good luck Man City as well to the Champions League tonight. Let's hope that they get into the final. That'd be nice, wouldn't it? Don't like Man City too much, but it'd be nice to have 2 Manchester teams in the finals, wouldn't it? That'd be good. Any questions now about anything? This question does lend itself to MATLAB. It's the best one for having a little MATLAB program to help you with it. It does. MATLAB shows everything. The root loci will give you the whole lot. You've got to drag your mouse along it. It'll give you all the graph. Move your mouse along and it'll work. It gives you the complete thing, but the root loci command just does it. And that's, you can't see them very well on this, but this is the sort of typical thing you get. There's a root loci sketch there, and I've used the mouse to drag it to a point there, and it tells me what the answers box here. I apologise for it, just doesn't work on white, this camera. It's too much light here. But it's not, we'll have it a go. If you're struggling with this, just email me and I'll send you the code to do it with, so you can see the answers. Just need five lines of code. Just run it. It does show, so what you say, it doesn't show the curved lines, it does. Okay, so thank you very much for listening now, and good luck with the exam, and see you in next September. in Salford, hopefully. I think we'll definitely be in Salford next September, won't we? But it's whether we'll have lectures online or lectures in Newton, I don't know. It's 50-50. So on that note, I'll stop recording now. Thank you very much. And this is my last lecture for this particular session, so it's quite nice for me. I've kept a lint Easter bunny specially spare, so I'm going to kind of have a bit of lint Easter bunny now, stuffed myself with that, having done my last lecture of this current academic year. And I hope you all have a nice, happy exam. I hope you all get a nice, happy mark from my part of the exam paper. So good luck, and I'll stop recording now. And if you've got any questions, feel free